before presenting its solution. So here we're talking about a potassium sulfate solution, and we're given the form of the partial molar volume for the potassium sulfate solute, the form of its partial molar volume, and we're being asked to find the partial molar volume for water. And so let's review how to do this using the Gibbs Do Him equation. It's a little involved, but I'm going to go ahead and present it for you. So the Gibbs Do Him equation tells us that essentially the partial molar volumes of the two components of the solution are related to one another. So we can take the number of moles of the potassium sulfate, I'm just going to use a K to represent that, times the change in the partial molar volume of the potassium sulfate, plus the number of moles of the water times the change in the partial molar volume of the water. That equals 0 according to the Gibbs Do Him equation. Now, essentially what this problem has done is it's giving us a formula for the partial molar volume of the potassium sulfate, and it's asking us to find the formula for the partial molar volume of the water. So we're going to rearrange this equation and solve for the partial molar volume of the water, or at least its differential. So the idea is that we want to integrate both sides of the expression, okay, to give us the partial molar volume of the water. Let's think about that a little bit. So the format that they've given us, this new B here, it's the partial molar volume where Z is this ratio of B over B0, where B is the molality of the solute and B0 is the standard molality, which is 1 molal. So essentially Z is the molality, and so we're going to treat it as such. So instead of using this Z, I'm going to treat it as if it were the symbol for the molality, which is B. And so before we substitute in, I'm just going to go ahead and write that down. I'm going to write this VK as a number, I'll call it C0 plus the number C1 times B to the 1/2. So C0 is the 32.28, C1 is the 18.216, and B is the molality to the 1/2 power. So what I'm going to do is I'm going to take the differential, and that's going to give me 1/2 C1 times B to the -1/2. So just taking the differential expression here. Then what I can do is, and then we'll write that as now dB. So the differential of this would be, of B to the 1/2 would be B to the -1/2 dB. And so now we can express the right-hand side in terms of the molality. So I'm going to go ahead and substitute that in now. So we're going to go back to this line here. And then we're going to do a little bit of work on the concentration units. So I'll just go ahead and plug all this stuff in. We've got -1/2 C1 B to the -1/2 dB. And before we do any integration, what I want to point out is that there's a molality unit hiding here in the coefficients. Okay? What would be the molality of the solute? Well, it's going to be the number of moles of the solute divided by the kilograms of the solvent. Okay? And so we've got moles of solute in the numerator, and then we've got moles of water in the denominator. Well, we can convert moles to kilograms. So what we'll do is we'll multiply and divide by the molar mass of water. So then we'll have NK over molar mass times NW. So just multiply it and divide by the same number. Here, I'll just say that we've all got the same thing here. Now, this is going to give us grams. We want kilograms of solute. And so I'm going to make this minus MW. And then, so we want this to be, we'll have to multiply and divide by 10 to the minus 3. And that's going to give us our kilograms of water. And so now this factor in front, this is the molality. So this is equal to B. So what I'm going to do is I'm going to substitute that in, and then I'm going to distribute the B into this parentheses. And so we're going to wind up with minus MW times 10 to the minus 3, and then we're going to have this 1/2 C1, and it's going to end up being B to the 1/2 dB. So now we've got the right-hand side is a function of the molality B, and what we'll do is we're going to integrate both sides. So the left-hand side is going to be integrated from pure water to whatever the partial molar volume of water should be at a given concentration. The right-hand side will be integrated from pure water, which would be a molality of 0, to whatever concentration B we want. So this is going to give us the function we want, VW, minus VW star, which the problem gives us. It's that 18.079 cubic centimeters per mole. We have these coefficients out in front. This is the molar mass of water, okay, times 10 to the minus 3. We've got the number C1, and then when we do this integral, it's going to give us B to the 3/2 times 2/3. And so the 2 is going to cancel, and we're going to wind up with a 3 in the denominator. So this integral here, just the integral, is 2/3 B to the 3/2. And so this is the function that we were being asked to find. We need to still put the VW star over on the other side, but once you do that, that's the answer to this problem. And in the graphic, here's a plot. So this function right here, the red curve, that is this VK. So that's the partial molar volume of the solute. And then the function that we found, VW, this is that function right there. And we see that as the partial molar volume of the potassium sulfate goes up, the partial molar volume of the water goes down. And the point being that the two are related to one another through the Gibbs Do Him equation. And so if you can measure the partial molar volume of one of the components, you can find the partial molar volume of the other component by integrating the Gibbs Do Him equation. You can do that for partial molar volumes. You can also do that for chemical potential. Any partial molar quantities for a binary system can be addressed in this way. Okay, well, we are going to change gears here, and we're going to take a little diversion and discuss gas mixtures. And on this slide, I've got two main concepts. The first one, and they're separate from one another. It's a little confusing. It makes you think that this equation is related to these. I'm sure there's a connection, but this is something that I just wanted to get out there because we will be using it a little bit later in the presentation. And what I wanted to do was to show you where this this equation comes from, because we're going to use this equation a lot. And so I just wanted to reiterate, to kind of go back and show you that indeed these are things that we already know. So really, what I'm trying to convey right now is that you already know this equation, even though you think you don't know it. So let me go back and let's do a calculation for an isothermal. We'll make it it doesn't matter that it's reversible, so I can just say isothermal expansion of an ideal gas. And what I'm going to ask you to do is to calculate delta G for that. Okay, so delta G is going to be equal to delta H, since it's constant temperature, minus T delta S. Okay, for an ideal isothermal process involving an ideal gas, we know that delta H is 0, and then you may or may not recall the formula for delta S. I'm sure you've worked with it. It is plus NR, natural log of, I'll do VF over VI, final volume over the initial volume. And so we get minus NR, natural log of VF over VI. If you'd like, instead of expressing it in terms of the volumes, you can express it in terms of the pressures. So we can do PF, actually it would be nRT over PF over nRT over PI. Right, so I've just substituted in the ideal gas law for the volumes. The nRTs cancel, okay, and this is going to give you minus nR natural log of PI over PF. It's kind of annoying to have PI over PF, so what we'll do is we'll use a logarithm trick. We'll bring down a minus sign, so that's going to give us plus NR, natural log of PF over PI. Okay, so this is actually an expression that we've used before. I just showed you that it comes from the things that we've already been studying. Now what I'll do is I'll contend, okay, you can write delta G as GF minus GI. In fact, what we can also do then, I'm going to change, what I'm going to do next is divide both sides by the number of moles. Now, let me do one other change of notation first. What I'm going to do is I'm going to let GF, I'm just going to call that G, GI, I'm going to call G0, PF will go to P, and PI will go to P0. So just a change in notation. Nothing fundamental's changed. So this is going to give us G minus G0 equals NR natural log of P over P0. Next, I'm going to divide both sides by the number of moles. So I'm going to have Gibbs energy over moles, G0 over moles. Well, that's just the chemical potential. So I'll have chemical potential minus the standard chemical potential equals R natural log of P over P0. And of course I dropped my, right here, you probably caught this, I left out my T. And put it in real quick right there. And so finally, just rearranging. We get this expression, okay, which we're going to be using quite a bit. So I just wanted to show you that indeed we have already explored everything leading up to this formula. What this is, it expresses the chemical potential of an ideal gas at some pressure P. It's referenced against the standard state chemical potential, and this is the correction factor. Okay, so the chemical potential at some pressure P is referenced against a standard state chemical potential plus this correction factor. And we're going to use this quite a bit. Okay, so a separate a separate thing is the topic of ideal gas mixing. And so the idea here is we're taking pure gases, pure ideal gases, and then just mixing them together, and we're looking at the thermodynamics of that process. This type of simple mixing is always spontaneous because the entropy increases. For ideal gases, the process has delta U and delta H equal to 0 because ideal gas particles don't interact one another, so the energy does not change when you mix them together. If the temperature doesn't change, the energy of the ideal gas doesn't change. Here we've got the formulas for calculating delta G of mixing and delta S of mixing. We could, I think I'll go ahead and show you where that comes from. So first off, if delta H is 0, then delta G of mixing is just minus the temperature times delta S of mixing. So let's calculate the delta S of mixing for an ideal gas, for mixing ideal gases. So what you're essentially, the way to think about this formula that I'm deriving is that you've got a gas, some number of moles of gas A at temperature T and P is going to be mixed with some number of moles of gas B at temperature T and P and pressure P. So you remove the partition between them. Gas A will expand to fill the full volume. Gas B will expand to fill the full volume. We're going to have a new, we just combine the two pressures don't change because they were the same before. It's now that the two pressures, the two partial pressures, add up to the total pressure that we had before, and the temperature doesn't change. So we can think of this as a gas expansion problem where gas A is confined to volume A and then it fills up the rest of the volume. Gas B is confined to volume B and then it expands to fill the total volume. And so I'm just going to go ahead and set that up. So for the expansion of an ideal gas, let's say two components, gas A expands, and so this is the entropy component for gas A. It's going to be whatever that final volume is divided by the original volume plus a term for gas B that expands, so number of moles of gas B times R natural log of V over whatever the original volume for gas B was. Substituting in the ideal gas law, we can write this as NA RT over P, where this is, and then we can do the same thing for gas, for the denominator as well. Well, actually, there's a difference. Let me scratch that here. It's NAR natural log. This would be NA plus NB RT over P. And then this would be, in the denominator, we have NA RT over P. We'd have something similar for the second term. I'll just write that down. So what I've done is I've taken the total volume in each case and I've replaced it with the total number of moles times RT divided by the total final pressure. So if you look here, the total final pressure is also P. The denominator is for the initial conditions, number of moles of component A times R times T divided by its initial pressure. And I did the same thing for this term. So what you see is the RTs and pressures all cancel. And that gives us NAR natural log of, this would be 1 over the mole fraction of component A plus NBR natural log 1 over the mole fraction of component B. So I'm going to flip things around and factor out a minus R. So notice I took the reciprocal inside the logarithm for both terms, and that gave me the minus sign. Factored out the R as well. Next, what I'll do is I'll divide both sides by the total number of moles. So that's going to get me this intensive quantity. So this will now be the change in entropy per mole of mixture formed. If I divide each of these terms by the total number of moles, it's going to turn those into a mole fraction as well. So we get XA ln XA plus XB ln XB. And then finally what I'll say, this generalizes to an arbitrary number of components, where you can do this for as many gases as you want. You just add up the same term over and over again for each gas. So then taking this expression and substituting it in for the change in the entropy of mixing gives you the Gibbs energy of mixing, which essentially multiplies it by a minus T. And so you get RT times this sum. What I'll point out is that because mole fraction is obviously a fraction, it's less than 1, every term in this sum is negative. You multiply that by a negative, that means that delta S of mixing for ideal gases is always positive. So the entropy always increases when you mix ideal gases. Likewise, for the same rationale, delta G is always less than 0. Mixing is always a spontaneous process. This type of simple mixing is always a spontaneous process. Well, here's a plot of delta G for mixing. You see that it becomes most negative for a 50-50 mole fraction mixture. Let's see. Here we have the delta S is just the opposite sign and off by a factor of temperature. So it peaks. The amount of entropy produced peaks for a 50-50 mole fraction mixture of ideal gases. Here, these problems are rather straightforward, so I'm simply going to leave them for you as an exercise. You essentially need to calculate delta G and delta S of mixing when you combine this many moles of each of these gases. It's a little tedious to execute these formulas, but I think I'll just leave it to you to work through that on your own. You'll find it's not that difficult once you get the formulas down. Let's see. So this is exactly what I've derived the formula for you, but this is really the same problem. So I think I'm just going to leave this as an exercise for you as well. It's really just carrying out this this sum for the conditions given. They don't give you any numbers, but you can actually still do the calculation, right? So coming from this formula, if you combine equal amounts of gases by mole, that means that the mole fraction of each component is going to be 1/2. And so you're going to wind up with minus R 1/2 natural log of 1/2 plus 1/2 natural log of 1/2. And so you'll get minus R natural log of 1/2. So you can actually do the calculation even though they didn't give you any numbers in this problem.